just see this screen right now. So it'd be fun. Yeah, okay, so I'm gonna be talking about the output data structures for ratpac. Talk about basically there's two data structures. I'll review a little bit about the DS file and how to write it out and the simplest way of reading it to the browser. And then talk about the end tuple and end with showing some examples of how to add things to the end tuple that you may want to save for your experiment. So the ratpac-two simulations have two main output formats. First is the DS, which has all these custom structures that we talked about the other day. It can have all the full simulation, reconstruction, everything details. And as we've mentioned, this is sort of more complicated to work with. And you really only want to use this for a specific analysis where you can't get by with the end tuple itself. And the end tuple is just a simplified flattened root T tree that has, all of the most important variables for your analysis. And the goal should be to basically try to define your end tuples to contain all of the info that should be needed for pretty much all of your analyses. Most of the time you should be using the end tuple. But first, I'm still going to talk about the ratDS in case people, need to use that. This is just a review, I think, on these slides from my previous presentation for this. But, the DS is the data structure. It has this top level container and then data structures which can contain everything that you need in your simulation for the event, the truth info, tracking info, whatever. And then about a little bit about the fact that there's a C++ interface to retrieve information from the root file that's produced. So yeah, it represents and holds all of the information for your physics event, and it provides the interface for things for you to create the physics events and write information to the physics events. So the top level container is this ratDS root structure, which represents one physics event, which, as we mentioned, was defined by your generator. It can contain multiple particles, multiple, detector events, and that holds lists of the custom data structures within the ratDS root that hold all of the information. The event info that represents your detector event is the EV, and the monocardinal truth, which the EV can have multiple per root event. And the truth info is only one per root event, and it contains the sort of true simulated information. And then you also have calibration info as well. So this was just my little diagram showing sort of the structure of the things contained in the root, top level container, and the things contained in each of the MC and V and cal containers as well. So the root files are written out using the DS writer class that's located there in the code, and it just writes the DS root files directly to a root file, keeping basically all of the same structure that is within the ratDS, as we talked about before. So it writes a T tree named T, which contains the root objects for the event level info, and under those root objects are all of the other objects that is contained within it. And it also writes a run T tree, which contains the run objects for the run level info. And it does the ability to autosave as you go, and it will write out a root file. So to do this in your macro, you just have to write 2 lines or even just 1 line. The proc out root is the processor that writes out the output file, and then you can add a line to your macro to define the macro name, or you can leave to define the output file name, or you can leave that line out and you can use the -O option when running the file to define the output file name. Or it will, if you don't define the file name, it will just give it some default output name. So in ratpac, there is an example that we've seen before already. Uh, so just simulating electrons. And so want to try simulating this and looking at a root file, can either add an additional line to define the file name or write with the -o option to produce a specific file name. And that will run and produce a DS file output. So I actually might try to do that. And it should be pretty quick to generate these things. And so the rat DS files, assuming you have rat installed, you should be able to open them in a T browser and to quickly look at the information. It's doing. Root T browser. And so you can see here that the root file has exactly the objects in, so this T tree contains the DS object. The DS object contains the MC caload and EV objects under as well. So this this isn't how you should analyze things really. We'll talk about opening this in more detail in the next talk. But if you run this, you can open up and click on various branches to take a quick look at things like, for example, the total charge in each of your events. And if you do click around, you might see that only certain branches are able to be opened because you can only open things with simple data types in your T browser, and branches with custom classes, you'll need the DS reader, which will also be required for any sort of more serious analysis. And again, yeah, you can only even open these files if you have ratpac installed. Talk a little bit more about DS files later. But next, we'll talk about the ntuple files. So most of the time, you should be using ntuple files. They're a simplified, flattened version of the DS that contains the most important details. So the code, all of the data that is in the ntuple comes from the ratDS structure. And so the processor obtains all of the data from the structure to fill three main trees. There's the meta tree, which stores the run level metadata, things like run number or calibration info. There's the output tree, which stores the event by event data, like PMT hits, tracking info, or reconstruction quantities. And then there's also an additional optional waveform T tree to contain the digitized waveform data. So the meta tree has information, the idea is to contain meta information about the setup of the detector or the run itself. Things like, this has a list of several of the things that are stored in here, like the run ID, the type, things like your PMT information, all the PMT IDs, their positions, whether they were online or not, and information about your digitizers if you have them, like the window size, sample rate, things like that. And it's mostly obtained from these classes in the ratDS structure. Then you have the output tree, which is sort of the main tree that you'll be looking at. It contains all of the event info, things like the one thing that I think is probably worth mentioning, the event ID is numbered 1 per DS root object. And then you have the sub EV, which is numbered one per DS EV, starting at 0 and incrementing for every EV within a root object, and then resets back to 0. So if you have something like an ambi event where you have, a neutron or a gamma and then a neutron, the first thing you simulate will give EV ID 0, and then the sub EV for assuming they both trigger your detector and create an EV, the sub EV for your gamma will be 0, the sub EV for the neutron will be 1, and then the next simulated event will have EV at 1 and move on. And then it'll have things like the number of hits, the trigger time, timestamp, all of your reconstructed information and classifier results and things can go in here. I didn't think to put this in the talk, but it was mentioned earlier that I think it's a good point that all of your reconstruction results automatically get written with the sort of reconstructed quantity underscore the name of the figure into the output n tuple. And then the MC truth info is also written here as well. Things like the PDG code, the position, time, direction, energy, etc. And other true information. And so you can see the documentation has a lot of information about what is written out here. And there are also optional outputs that you can control in your macro, including the PMT hits. So each individual PMT will give each hit PMT will get an entry in here with the ID, time, and charge of the hits. You can have digitizer info saved and as well as tracking info saved into the n tuple as well. And then finally, there's the waveforms tree, which is also optionally saved based on setting an option in the macro, which includes, the digitized waveforms, the event IDs, and things like that. So it has pulse times and charges as well. So that is sort of some basic information about the n tuple. I'll talk about opening one later, but next is just some sort of a look under the hood at what's happening for the more advanced users who want to know what things work and might want to add things to this. So it's written out using this out n tuple processor, which opens the files, creates all of the T trees and branches, takes in your, what your settings were to decide whether to create the optional branches or not. Then it will go through the rat.ds data structure and fill all of the variables based on the data structure, what's in the data structure. And then it fills the output tree for each event and fills the meta information once at the end of a run. And then it writes out the file and closes it for you to analyze later. So to do this, to use this processor, you just add basically, the same as before with the out root processor, except it is now out n tuple. And you can add a second line to specify the file name of the n tuple output, or you can use the -o option again. And then there are also a whole bunch of different lines you can add to include the optional settings, things like tracking the Monte Carlo particles, PMT hits, digitized waveforms, whatever. A couple of them are by default true, so you can use that to turn those storage off if for some reason, you really need to save space or didn't need them at all. And you can also write out both the DS and n tuple files simultaneously. If you had, for your experiment, some people need to use the DS and other need to use the n tuple. You can write both out for this, so they have the exact same files for the exact same simulated events in both formats. Okay, so again, looking at the example macro, you can take this macro and then edit it to do live. Include the n tuple processor as well. And about these things pretty quick. And so once you do this, the nice thing is with the n tuple files is no matter, as long as you have root, you can open these in your T browser, you can look at it, regardless of whether you have rat installed or not. So you can just take a look at the T browser again. T browser is just a simple way to look at things, real quickly. And the next stop will be looking more. Oh, I messed something up.
You left out root, didn't you? What, you left out root in your.
Oh, I named the outroot file the same as the entity file. You can get both from the same macro. Yeah, and so because the n tuple is a flat tree, you should be able to open any of the branches easily. Follow in its.
Yeah, you didn't run any waveform processing, so.
Yeah.
Filled.
Yeah,
So those will be, almost none of these will be filled, but the MCM should be filled.
yes, you can see CPE positions, T hits, things like that. So very quickly open up a file, look, at that basic information just using a T browser. In and again, the next talk will be more specifics about looking at this. So another thing that would be probably a common need for experiments is adding a new branch. So if you make a processor that you think is useful for anyone using ratpac, you can add this new branch into the ratpac repository itself. Just by, you have your processor or whatever variable that is in the ratds, and then you edit the out n tuple proc. You find the branch where all the branches are created, you add your branch for the variable you want, and you find where all of the variables are filled by getting the information from the DS. You get your information from the DS, fill the variable, it gets filled, you rerun the macro and look at the output to see that everything makes sense. But I think in a lot of examples, you may have something that's specific to your experiment. And so we haven't talked about creating your own private experiment, which we will talk about tomorrow, but I'll use EOS as an example to show that the existing out n tuple processor contains functions that allow you to extend the n tuple in your own private experiment for variables that are specific to your experiment. So they have these assign additional meta addresses for branches in the meta tree and assign additional addresses for branches in the output tree. Functions that you can overload, and then fill meta, and fill event, which fills the data in those trees. And so if you're going to create your own n-tuple processor, here is the example from EOS, n-tuple proc in EOS simulations. So you create your own processor where you inherit from the out n-tuple processor. You define the name for your processor. In our case, we defined it as EOS n-tuple, and that's what you use to call this specific n-tuple output instead of the default ratpac output in your macro. You overload those functions that I mentioned before, the assign additional meta addresses or assign additional addresses. This shows that we wanted to keep the source position and source rotation or direction, basically, for some of our sources. And then you overload this fill meta or the fill event to where you define, in this case, you get the information from a database and you set each of those variables to the source positions from your database. And then the out n-tuple, this processor will include those additional variables in your n-tuple. So yeah, I think that is all that I have. Basically conclusions. There's two main output formats, the DS and the n-tuple. DS has, more functionality if you really need it, but most of the time you're probably just going to be using the n-tuple. And both of them can be produced from the macros and can be extended based on the needs of your experiment. So, are there any questions?
Might have a quick tip. So you showed the example with the out root and out n-tuple. If you don't specify a file name within the macro, and you add that -o, if you don't add a .root, you call it electron.root. If you just call it electron, it's going to create the files with the right extension for you. So it's going to create an electron.root and an electron.n-tuple.root. So people want to test that out. That is kind of useful if you're trying to do something.
That's useful so you don't accidentally write both to the same file name like I just did.
Ready to go?
Yeah.
Maybe a quick PSA, I just posted to the summer school